Hello everyone, this is Dr. Lennon, and I just want to go over a few physical applications of integration to some other disciplines besides just purely mathematics. So the first one here is finding the mass of a bar given a density function. So the way that is accomplished, you can get, so given a density function, the letter they like to use is the Greek letter rho of x. The mass of the object is given by, and this is along some line on a closed interval, let's say a to b, is given by m is equal to the integral from a to b of your density function rho of x dx. So that's exactly what we're doing here. So in this example, what we want to do is we just want to integrate on the interval with the density function that's given. So we can go ahead and set that up right here. So this is kind of the general idea, and for this specific problem it's going to look like the integral from pi over 6 to 2 pi over 3 of this 1 plus the sine of x dx. And this is fairly easy to integrate, right? The integral is just going to be x minus the cosine of x on the same interval from pi over 6 to 2 pi over 3. And that can be evaluated pretty simply. Basically what you get is you're going to get in the first one pi over 2 plus a half, and in the second part we're going to get, so I've already combined them. Sorry, I was reading my notes and I misread. So it'd start with 2 pi over 3. I was reading the wrong line. 2 pi over 3 plus a half, because the cosine of 2 pi over 3 is going to be negative 1/2, so we have two negatives there. And then we're going to have minus pi over 6, and then cosine of pi over 6 is going to be the square root of 3 over 2. And again, that can be combined as one big fraction actually. 2 pi over 3 minus pi over 6 is going to be pi over 2, which is what I was writing down the first time. So anyway, this can all be combined as square root of 3 plus 1 plus pi, with everything being divided by 2. So pretty straightforward application. Just plug everything in and do the integration, and not too much to worry about there. Okay, why don't we do another one of those, just a really quick one. So let's say find the mass of a thin bar with density function rho of x is equal to 1 plus x cubed, so just a polynomial example, on 0 less than or equal to x less than or equal to 1. So again, the setup is exactly the same as in the problem above. That's all we have to do is integrate this density function on that interval. So our mass is going to be the integral from 0 to 1 of 1 plus x cubed dx, and that has an antiderivative of x plus x to the 4th over 4, just using the polynomial rules to establish that. And from 0 to 1, we're just going to get 1 plus a 4th, which we can write as 5 over 4. So again, these are very quick. The only thing that's going to make them difficult is if the density function involves something that's tricky to integrate. Other than that, the setup is not difficult at all for these types of problems. Okay, so another application that comes to us from physics is understanding work. So work done by a variable force is given by an integral also. So let's just talk about that. It's really the same thing as the density we just did. We just need a force function. So the work example here is, so the work done by a variable force F, meaning your force can be written as some type of function, along a line from A to B. It's just going to be given by the integral from A to B of f of x dx. So we could say work is the integral from A to B of capital F of x dx. And that's what we're going to use for this problem. So we have a force of 60 newtons required to stretch and hold a spring 0.2 meters from its equilibrium position. So the first question talks about Hooke's law. So basically Hooke's law just says that springs behave according to direct variation. So if you have some spring, you can always write the force equation as just some constant pertaining to that spring times x. So if you have one data point, you can determine what that constant is and use it for future values. So that's what they're telling us here. So when we're looking at part A, we have a force of 60 newtons required to stretch a spring 0.2 meters. So that 60 newtons is going to be equal to exactly k times 0.2. So we can divide by 0.2 when we see that 300 is the value of k. So now we have our essentially force equation for this particular spring, which is just going to be F equals 300x. So that's what we're going to use when we try and determine work. That's our capital F of x equation, 300x. So B is asking us how much work is required to compress the spring 0.4 meters. So that's pushing it inward. So we would think of that as a negative 0.4. You could actually do this integral with regular 0.4, stretching it rather than compressing it, because essentially with this equation, when you do the antiderivative, you're going to end up squaring it. So the work required to stretch it is going to be the integral from 0 to negative 0.4 of 300x dx. And that's a very easy integral, right? It just has an antiderivative of 150x squared. Again, that's because 300 divided by 2 is 150. So when you're evaluating this, we just get 150 times negative 0.4 quantity squared. And let's see what that comes out to, some amount given in joules. So we have 150 times 0.4 squared. So that's going to be 24. So the answer to part B is 24 joules. Let's go ahead and look at C. What did they want for C? They wanted us to stretch the spring 0.5 meters from its equilibrium position. So really that's not too much of a different problem. The work here would just be given as the integral from 0 to 0.5, positive 0.5 since we're stretching it outward, of this 300 x dx. And again, that's just going to be 150 x squared from 0 to 0.5. And I believe that gives us 37.5. Let me just double check. Yeah, 37.5 joules here. And then the last one is not so difficult. It says if your spring is already stretched out 0.2 meters from the equilibrium position and you want to stretch it an additional 0.2, what would that work be? So that work would be just going from the 0.2 that you started away to the 0.4 outward that you're trying to bring it. And the same equation there, 300x dx. So we end up with 150 x squared from 0.2 to 0.4. And let's go ahead and figure out what that is. Really, that's all we're essentially doing is 150 times 0.4 squared minus 0.2 squared. So what does that come out to? Comes out to 18 joules. So 18 joules for the last part. But again, really a relatively simple problem. The formula is kind of like identical to the formula we had for finding the mass of an object given a density function. This time we're just trying to find the work required given a force function. And Hooke's law gives rise to a very simple force function. Okay, for our next example, we're looking at the force required to force from water. So a lot of times these are considered like pumping problems. So the formula that we're borrowing from physics is the work here is given by the integral from a to b on some cross-sectional area. You can see the figure above. That's going to be the cross-sectional area we're thinking about, with the density of whatever we're pumping. In this case, it's water, so they give us 1,000 kilograms per meter cubed, times the force acting on it, which in this case is gravity, which is the 9.8 meters per second squared that you see. And then we need to multiply by the area with respect to y times the way that we're actually slicing it, d of y, capital D of y dy. So in this one, it's not so bad because we've just got like a cross-sectional area. So we're thinking about slicing it in terms of essentially the width. So what we want to do is we want to create a function where we can determine the width. So if you look at that trapezoid, what we want to do is we want to figure out a width function in terms of y. So the easiest way to do that is to think about this point here in the middle as your origin, 0, 0. And then this point, since that's 16, would be 8, 0. And if you think about the corner point, that would be up 24, and you'd be extending it 8 further meters, right? Because we're already kind of starting halfway to 16. And so this above right here would be 16, so it's going 16 more, which we've already gone 8 to the bottom corner. So the coordinates of this point up here would be 16, 24. So really, if you want to think about some type of width function in terms of y, so if you want to call this the length of any such segment given a y value w of y, what you're really trying to do is just figure out the x coordinate that we're at on this line here. So if we can find an equation of the line and then solve in terms of x, we'll be all done. So actually, this x function is not giving the width, it's giving half the width, right? So whatever equation we have, we're going to have to multiply that result by 2, and that will give the width. So first thing to figure out here is what would the slope of such a line be? Well, it would be 24 minus 0 over 16 minus 8, and you get exactly 3. So you know the equation of the line looks something like y equals 3x plus b. And then you just plug in one of the points, say 8, 0. So you'd get y equals 24. Sorry, 0 is replacing y. So we'd get 0 equals 24 plus b. So that tells us that the b value is actually negative 24. So we would have, as the equation of our line, y equals 3x minus 24. And if you want to solve for y, basically what's going to happen, we get y equals, we want to solve for x because we're integrating up. So what do we end up getting? Well, we'll get x, if you solve for that, is going to be 1/3 times y plus 24. So then our actual width function would be double that, because this is just the half of the positive segment there. So w of y, we would really want to say, is 2/3 times the quantity y plus 24. So that's giving us the width there. Okay, so that's the width. You would also want to think about, given a specific y value, how much the height would be, right? Because that's going to help determine our area function there. So given any value y, the remaining height that you're talking about is going to be that 24 minus y. Okay, so that's like your remaining height function in terms of the water that's acting on the dam. Okay, so then once you've got that, you've pretty much nailed all your setup work, and you can just plug everything into the work integral. So we'll just set up the integral and not evaluate it because it shouldn't be too complicated. It's just a polynomial, but the setup is the most important part. So now if we translate this formula, our work is going to be the integral. Again, we're going in the y direction, we're integrating now, so the entire face of the dam is starting at y equals 0 and going to y equals 24. So remember, we're using y values here. So we're going from 0 to 24. Rho is 1,000. In this case, the g is 9.8 meters per second squared. And then we have essentially the things that we have on the face here, the height function and the width function that we talked about. So this is going to be multiplied by 24 minus y, and then that's going to be multiplied by 2/3 times y plus 24. And that is the entire setup of the integral. So again, you can multiply this out and pull out all your constants and everything like that, and get the exact value, but I'm not going to do that here. It's really not so hard because, right, 24 minus y and 24 plus y is just going to end up being 576 minus y squared. So that's something that's very easy to integrate, but that's how you set it up. Essentially, you need to create a function in terms of y that's figuring out the width on the face as you integrate, and then also the remaining height. Okay, so let's go through one last one of the previous type. Again, I'm not going to do the integral, but we'll just set it up. So what we've got here is we've got a dam where the bottom half of the face looks like a semicircle, and we want to set up the integral again. So the same kind of concerns go. We have the semicircle, and we want to think about this middle point here is the origin. So if I call this 0, 0, in general, how am I going to think about my width, and how am I going to think about my height? Again, it's easier to think about vertically in terms of y. So if you think about the coordinates of any point, you're going to be getting a negative y value here. So your height, in terms of what you have left, your depth, is it's just going to be the opposite of your y value, right? If you have some y value down here, some point, well, actually, it's probably easier to think about starting from the bottom, right? If we start at the very bottom, that would have a measurement of 8, right? Because this is a semicircle, so this vertical line is going to represent the radius. So this has coordinates 0, -8, but that would actually be a height of +8. So basically our height function there is going to be, say, I don't know, h of y. That's actually just going to be -y. It's going to be the opposite of whatever your y value is. And that's going to indicate the depth in the dam. So the one that you want to figure out is the width function. And again, we could try to think in general, what are just the coordinates of a point over here? Well, we know this point right here is going to be 8, 0, right? Because the circle has radius 8. But what would it be if it were somewhere down here? Well, it would be the equation of wherever you're at on your circle. So this is a circle. We've established that the center is at the origin. So the equation of a unit circle is quite easy, right? It's just x squared plus y squared equals the radius squared, which in this case is 64. So we want to solve for x. So x is actually just going to be the square root of 64 minus y squared. So that would give you half of the width, right? If that is your x value, it would be giving you exactly half of the width from here to here. So you want to double that to figure out your actual width function. So our width function here, w of y, is going to be 2 times the square root of 64 minus y squared. And multiplying these two things together, that's how we get our cross-sectional area. So the work that we want to do for this problem is just integrating from -8 to 0. And again, we need to multiply rho by g. So again, we're going to have 1,000 times that 9.8, and then we're going to multiply our two functions here together. So we're going to have -y, and then we're going to multiply by 2 times the square root of 64 minus y squared, and differentiate, and that's with respect to y. So multiplied by dy. Again, you can pull all those constants out to make it easier. So maybe I'll just write that down. So I don't know what 500 times 9.8 is. Let's see. That is 4,900. So really you can think about this as 4,900 times the integral from -8 to 0 of, I can probably actually pull out the negative if I want also, but I'll leave it inside the integral just because maybe it would help you in terms of, oh, and then I could bring the 2 out as well. I forgot to Well, I'll just leave it on the inside. And oh, no, did I bring that up? What did I do? I think I multiplied wrong. I think that 4,900 is incorrect. Let me check that again. So it should be 2,000 times 9.8. Yeah, it should be 19,600. I think I did a half instead of 2. So anyway, this ends up being 19,600 on the outside. But then we have negative y times the square root of 64 minus y squared. And how do you integrate that? Well, this is going to just be a u substitution, right? We're going to let u be 64 minus y squared, and then you're going to be able to take care of your minus y due to the u substitution, right? Because here du will be minus 2y dy. So you'll be able to get rid of that. And finishing that integral will give you the correct answer. So again, that's how you set up this pumping problem with respect to this shape of dam versus the other one. So anyway, we'll finish there. This is Dr. Lennon signing off.